Hello? Okay, so let's say a bit for my mic, but welcome to my talk. So my talk is about building next-gen security tools with reverse engineering Trilogy. Okay, so my name is Quynh, and I'm working for one university in Singapore. And my main research area is on a low-level stuff like operating system, virtual machine, binary analysis, and reversing. And I happen to be the author on three frameworks you see on the screen: Capstone disassembler, Unicorn emulator, and Keystone assembler. So that's a quick question. Anybody here is using any frameworks on the screen here? No? Okay. So if you're doing reversing, you're doing malware detection, you write exploitation, or you play CTF, it's a very good chance that you use some tools that use some of my frameworks here inside. So in this talk, I introduce all of my works, all my frameworks, the motivation why I did all of this, how these frameworks are designed, implemented, and how community build very exciting, very innovative tools on top of these trilogies. And finally, I will also introduce some of my own works built on top of this trilogy. Okay, so looking at reversing tools, all of them, be it binary analysis, debugger, or exploit development tools, they all build on three frameworks. First one is disassembler. Second one is emulator. The last one is assembler. But unfortunately, before I created my three frameworks, there's no single frameworks for disassembler, for emulator, for assembler that is multi-platform and multi-architectures. So there's no such a thing. So I decided to step up and create one by one. So for disassembler, I created Capstone. For emulator, I created Unicorn. And for assembler, I created Keystone. And all of them are open source, run everywhere on all kind of platforms, and run in many, many CPU architectures. So all these three frameworks complement each other, make a complete set of frameworks, and I call it reverse engineering trilogy. So we went a long way since 2013 when I started build Capstone, and after that I build Unicorn and Keystone. So far we have we open source on the projects, and we have 250 people contributed code. We had so far 33 releases, and have totally 40 language bindings for all of these three frameworks. And this trilogy are widely used in many, many big companies like Intel, Google, Apple, Microsoft, Qualcomm, Samsung, Cisco, FireEye, Palo Alto, Symantec, and a lot of other companies. And on top of this trilogy, community built about 400 applications, 400 security tools that they public. For those not public, I don't know. And among 400 tools, there are many become de facto tools for the industry. So another fun thing is that anybody here use IDA for reversing? Okay, so every year IDA they organize a contest named Hexray plugin contest, so people can write plugins for IDA and submit to them, and they judge and they give out the prize. So for last year, 2016, the top 4 prize we contributed to 3. So you can see here on the screen. So the first prize from Shellfox, they use a Capstone disassembler inside. The third prize built by me. Key patch use Keystone, and the other third price label-less also use capstone inside. So, because I have some academic background, so I'm very happy that all of my frameworks are very well cited in academia. So there are many papers, many bachelor degree, master degree, PhD thesis used and cited my Trilogy. And they also very widely used in many workshops and many training courses in industry. And capstone, unicorn, and Keystone also appear in books, in comics. So just on comics you can see. Here's a comics. So some hackers, they try to reverse some shellcode in ARM, and they use capstone. It also appears in a Mr. Robot series. So you can see that some guy who, okay, the main character, they try to reverse some firmware, and inside that they use radar, which is like defector tools for reversing. And radar use capstone by default. So you can see that all the assembly output on the screen come from capstone. And one more thing. Last year we have a very excited competition in Vegas named Cyber Grand Challenge. I think everybody here know, right? So that's the first ever competition organized for machine to automatically find and exploit vulnerabilities in software. And there are 8 teams in the final. And I'm very happy that most of the teams, they build many small tools in the core, and most of them use either capstone or unicorn or keystone inside. So here's one example. So the third prize team named Shellfish, they build Anger, which is a very, very good tool for binary analysis. And inside they switch from some engine before they switch to unicorn, and they said that unicorn help to improve the performance up to like 600 times. And finally, it's very funny that they use a unicorn framework inside some APT malware. So here's a screenshot you can see. From Kaspersky, they said that Surface use a unicorn inside. Okay, so the first one, Keystone Disabler, started in 2013. So that started because on that year I have a talk in Black Hat, USA, and presented one rope gadget tool, which is an advanced tool for exploitation writer to file rope gadget in a smarter way. And this tool has few steps, but the first very important step is to collect all the gadget given the binary. You get out all the gadget in assembly. And after that, it tries to generate SMT equation and send it to the SMT server and get back the gadget for you. So this assembler is fundamental because you need that to collect all the gadget from the binary. So this assembler is some kind of software that given the binary as the input, as output, you get back the assembly code, which is very simple. And this assembler framework is the layer, the core layer at the bottom of all the binary analysis tool, debugger, and exploitation development. Unfortunately, at that time, my tool works very well. OptiRope works very well for Intel. And after that, I decided that I need to support other architectures, ARM, ARM64, and MIPS. And remember that we need this assembler, right? But unfortunately, in 2013, just no good disassembler even for Intel. So some public open source ones, they support Intel but very poor. They do not support the latest instructions. And they have a very limited license. And at that time, I want to make OptiRoad to support ARM, ARM64, and MIPS. But at that time, there's no framework for all these architectures. And for something you can find, they are have very poor quality, and they do not support Windows, and the license is very limited. So I wanted a new disassembler with this requirement. I want to have something run on own platforms, on own operating system, be it Windows, Linux, Mac, iOS, Android, and so on. It should work for all the popular architectures, be it Intel, ARM, ARM64, MIPS, PowerPC, Spark, and so on. It should support the latest instruction set, which is hard because the CPU vendors, they frequently introduce a new CPU generation. And when doing that, they add new instruction set. So it's very hard to catch up every year. And it should have a very clean API that is doesn't depend on platform, doesn't depend on architectures. It should have core in C, but support all the high-level language like Python, Ruby, and Java on top. So I can easily write my tools in Python, for example. And the disassembler should be compact enough so I can embed it inside the kernel or embedded system, which is have very limited space. So the point is there's nothing at that time. So I decided to step up and build Capstone. So you can see that what I wanted is a lot. I want to have many features, but I want to do all of them in few months, not years. Because naturally, if you build from scratch, it takes years to build the disassembler for only one architecture, for example, for Intel. It doesn't count all other architecture that I want. So to build all of them, to build the new disassembler with all of these features, it takes a lot of years, not months. So the only choice is to base on something already available. And after that, open source it for people to use, so people can contribute and improve it. So I fork LVM to build Capstone. So for those who don't know, LVM is an open source project for compiler. And it has huge community and backed by many companies, big companies, including all the CPU vendors like AMD, Apple, Google, Intel, IBM, ARM, IMG Tech, NVIDIA, Qualcomm, Samsung, and so on. It supports multiple architectures because all the CPU vendors want to build compiler for the CPU, right? So they support LVM to make the compiler for their architectures. So LVM run on all the popular architectures, that is Intel, ARM, ARM64, MIPS, PowerPC, Spark, and so on. And it runs on all kind of platforms. It runs on Windows, Linux, Mac, BSD, Android, iOS. So the reason I choose LVM because LVM already has disassembler inside. So inside LVM, there's one core component named MC, which has all the important part of LVM built around it. That is compiler, assembler, disassembler, debugger, just-in-time compiler built around MC. And MC has disassembler inside. So I can fork LVM, I can reuse MC component to build a Capstone. So there are many advantages if I do this. First one, LVM code has very high quality. So Capstone would have very high quality as well. The disassembler inside MC or LVM is built and maintained by top experts from each CPU vendors. For example, the disassembler for x86 is built by Intel. Who can do better than that? No, right? The disassembler for ARM and ARM64 built by ARM and Apple. Disassembler for MIPS built by their own CPU vendor. Disassembler for Hexagon built by Qualcomm, the creator of Qualcomm CPU. System Z built by IBM. PowerPC and Spark, not by the CPU vendors, but by community, but they are very active on that. So, because of this, all the new injection, whenever the CPU vendors they produce a new CPU, they quickly add this new injection into the LVM. And all the bugs are fixed very frequently. So it's good that you can fork MC to build custode, but there are many issues. It's not easy. First of all, MC is like a big spaghetti. It makes a lot of code inside. So it's not easy to get what you want now, because I only want disassembler. I do not want anything else. So it took me a lot of time to read the source code of MC, and I check out only the part I need. And because MC is written in C++, because LVM is written in C++, but I want to build a Keystone in C, so it's more compact and it can be embedded anywhere. So I rewrote all the MC code from C++ to C. Other things I need to do is that I need to expose the instruction internals that MC do not allow. So given the input as a binary, at the output you have assembly, but you also know, first of all, this instruction has like two operands. So the first operand is the register, the second operand is memory, and so on. So MC do not provide that kind of information, but Keystone can do. Keystone is also thread safe, so can write like multi-thread application with that. And I also build many options to customize. So you can build and customize Keystone, so you can optimize the size. So, okay, so here's some milestone for Keystone. The first public version was out in December 2013, and I made a talk in Black Hat 2014 on that, on the next year. And so far, Keystone is available in all the Linux distribution. That is Red Hat, FreeBSD, no, Red Hat, Fedora Core, Debian, Ubuntu, and so on. It's also available in all the BSD distribution, in Mac and in other package repo. So that was 4 years since I started Keystone. That's 4 years of development and maintenance. And so far I have more than 100 people contributed code to Keystone, with nearly 1,000 issued and pull requested. And people from, among the contributors, we have people from Google, from Apple, from Microsoft, from Intel, from Qualcomm, from Cisco, from FireEye, from Symantec. And so far, Keystone supported 10 architectures in the same API. That is ARM, ARM64, ARM64K, MIPS, PowerPC, Spark, System Z, TMS, Xcore, and of course Intel x86. And the good thing is that initially, the first version of Keystone, we fork LVM. So all the disassembler come from LVM, right? But over the years, people contributed, and we have two architecture not coming from LVM. That's ARM64K and TMS. They build from scratch, and now Keystone supports them, but LVM do not. So the core of LVM is the core of Keystone is built in C, and we support so far 18 language bindings. So you can write your own security tools in these 18 languages, and you can use Keystone. So that's all the language, all the common language you can find, even common list. So you can feel that you can write your tools in Visual Basic, PHP, PowerShell, Haskell, Perl, Python, Ruby, C#, Node.js, Java, Go, Rust, and so on. And among these bindings, I only build few. I only build Ruby. I build Python, OCaml, and Java. The rest was built by this enthusiastic community. So they are very, very active. So how to build your tools on top of Keystone? So Keystone exposes a very clean and very intuitive API. So you can easily learn from the sample in the source code and build the tool yourself. So here's one very simple in Python. You can see that first one you need to import Python, right? And then you specify which code you want to reverse, which code you want to disassemble. And then you initialize a Python object. So on this slide, you can see that I want to disassemble Intel 64-bit code, right? And after this, I disassemble the code, and I pass to this method. First one, the code here, and then the offset of the first instructions. And then I have a loop to print out the instruction, the arrest of every instruction, the instruction's name, and after that, the operands of instruction. And you can see at the bottom is the output of the program. So there are over 300 public applications built with Capstone that I cannot list all of them here because it takes like 10 pages, 10 slides for that. But here I pick up some of the most important, most prominent, some the factor tools in the industry. So you can see that's something like radar. They use Capstone as a default disassembler. Reliance and Hopper, they are two other reverse engineering tools, use Capstone inside. And the good thing is that they are Reliance and Hopper, they are commercial tools. Anger, a fantastic framework built by University of California. And the Selfish team, they use Anger to fight in the last CGC last year, and they won the third prize. They use Unicorn and Capstone inside. Quynh app debugger is a nice tool for debugging Windows. Rope Gadget is a tool for exploitation writer to find the rope gadget inside the binaries. Keystone, also coming from the same author, it's a very nice tool for dynamic binary systems. x86 debugger is another tool which is very nice for debugging Windows binaries. Snowman is a very nice decompiler built on top of Capstone. Beanwork, I think a lot of people here know that. It's a defactor tool to reverse reverse firmware binaries. Recon, so this one is from Google. It's a framework to do memory forensic. Cuckoo, it's very fantastic, awesome sandbox tool, open source, and they use Capstone inside. This is another tool to backdoor Windows Linux binaries called Backdoor Factory. I find that this one is very popular. Frida, another awesome tool for dynamic analysis, and they use Capstone inside. They heavily rely on Capstone. Home Foods is the father coming from Google. They also use Capstone inside. This one also coming from Google. It's very popular for pentest, for CTF. Nougat is a ART extension for Android. So Intel, they have their own build for Android, and they use Capstone inside. And finally, this nice tool coming from Jonathan, named WCC. It's a very special and amazing collection of compiler tools. So you can, for example, you do things like you can convert from Windows binary to Linux binary. So we can load that and run that on Linux, Windows binary. And there are a lot more you can find in the homepage of Capstone. So there are many things to do for the future. So I want to release the next version of Capstone this month, the version 3.0.5. After that, I release version 4.0, which is based on the next branch. It's dragging along for too long times. And I want to catch up with the upstream LVM to update, so Capstone can support the latest instruction from LVM. And finally, I plan to fork the new branch for version 5.0 with some very new exciting features that I have in plan. Okay, so here comes the second framework of Unicorn. Okay, Unicorn is the emulator. So it can emulate the binary instruction binary in software. So you don't need the physical CPU to run binaries coming from other architectures. For example, your laptop is is Intel, right? It's x86 machine. You can use a CPU emulator to run binaries coming from ARM or ARM64, for example. And there are many applications for CPU emulator. So you can emulate the code without having the real CPU. You can use this feature to safely analyze malware code because you do not physically run the machine code, the malware code on the physical machine, but run in the software emulator. And there are many applications for CPU emulator in code verifying, in decompiler. So here's one idea on how you can use emulator. So you can see that on the screen there are two code, the left side and the right side. They look very different, but actually they do the same thing. So the idea is that malware, they transform the code on the right side, which is very simple, to the code on the left side, which is very complicated, but they do actually the same thing. So by doing this, they can cheat the AV, for example. The AV cannot recognize the code on the right side anymore. So there are many ways how can you recognize the code on the left side is actually the code on the right side, and one way is to use an emulator. So you throw the code on the left side into the software emulator, run it. After that, you check the context after the code run, and you can see that how the context is changed after the code run. And you compare with the context of the code on the right side, and you see that the code on the left side even is very complicated, but it does exactly the same thing with the code on the right side. So that's one way to prove the equivalence of two very different code using software emulator. So now you want to build a new CPU emulator, but unfortunately there are a lot of work because you need to have very good understanding on the CPU architectures. You need to understand all the instructions that you want to emulate, and that's a lot of work. So before Unicorn, I looked at some software emulators, and I did not find many things. So I only found some emulator for x86, and even that, those I found was very poor. They only support very limited setup 32-bit instructions. There's no support for Intel 64-bit, and the performance is horrible. Besides Intel, I look at other architectures, there's nothing. There's no software emulator for ARM, for ARM64, for MIPS, for Spark, and so on. Nothing exists. So I want something new. I want something support all the architectures, all the popular architectures, ARM, ARM64, MIPS, PowerPC, Spark, and x86. And I want my framework, my emulator to run everywhere. Run on Unix, run on Linux, run on Mac, run on Windows, run on Android, run on iOS, run everything. And it support a new instruction. That's very important. It should have good performance because I want to have to emulate the code in very short time. And lastly, but very important, I want to have instrumentation in my emulator. So I want to know exactly at any moment what is going on when the code is running inside the emulator. So the same thing, I want a lot of things, but I don't want to spend too much time on that. I want to take just a few months to build my framework. And I do the same thing. I base on something already exists and fork it. And after that, I open source that for community to use and contribute. And this time I use Quynh. Quynh is a very popular, very widely used system software emulator for many architectures, and it's very widely used. It supports all the architecture you want, even some embedded system. It's already implemented in POC, so it's very easy to implement Unicorn on top of that. And it's already using the just-in-time compiler technique inside the Quynh, so the performance of Quynh is very good. So the Quynh actually is very complicated in the architectures, but we only want and care about one component, which is the CPU emulation, right? And I do not care about anything else because I do want only emulate instruction set and CPU memory access and nothing else. I don't care about other devices. I don't care about the bus, about the monitor, and so on. So I fork Quynh, and I pick only the CPU emulation part of Quynh and build Unicorn on top of that. There are actually many issues, many challenges when I build Unicorn. First one, like LVM, Quynh is a huge code. It's a mixed code inside like spaghetti. It's very hard to take only CPU emulation out. So it took me a lot of time to read the source code of Quynh to build Unicorn only from the CPU emulator. So I removed a lot of code and took only the code that I wanted to build Unicorn. The other challenge is that Quynh is actually a set of emulators. So when you build Quynh, you have a set of software emulator for each architecture. But we want Unicorn as a single framework that support all kind of CPU, right? So this one, it also took me a lot of time to re-architecture the code to have the single framework that support all the architecture inside one framework. The next challenge is that Quynh inside there has no instrumentation. You cannot instrument Quynh. And also because Quynh uses a just-in-time compiler inside, so it's very hard to instrument it. Because just-in-time compilers, they use many tricks. Hello? They use many tricks to make the emulator fast, so it's very hard to instrument. So for this challenge, it also took me a lot of time to build the fine-grained instrumentation layer for Unicorn from scratch. So I can instrument at every instruction. I can instrument at every memory access. I can also get notify on all the CPU exception, like interrupt or system call. The other challenge is that Quynh is leaking memory like hell, which is happen because they allocate objects, but they never free, they never close it. That is fine for Quynh because it's a tool. It runs and it stops. And when it stops, the operating system automatically free on the memory allocated inside. But because Unicorn built on top, Quynh is not a tool but a framework. So I care about memory leaking, right? So here it also took me a lot of time to find all memory leaking inside Quynh and fix all of them. So some milestone for my frameworks. I made a talk in Black Hat USA 2015. The first public release was in October in the same year. And the first stable version 1.0 was released this year in February. And the latest version is 1.0.1. And now in the latest code from GitHub, you can get a Unicorn, and you can build Unicorn natively on Windows using Visual Studio, which is impossible for Quynh. Quynh cannot build natively on Windows using Visual Studio, but Unicorn can. So it's 2 years of development and maintenance. We have 90 people contributed code and nearly 900 issues and pull requests on GitHub. And you have people from Google, Microsoft, Apple, Qualcomm, NCC, FireEye, Cisco, CrowdStrike, Cloudflare, Symantec contributed code for Unicorn. And so far, Unicorn supported 6 architectures. You can see on the screen. The core is EBU and C, but you have bindings for 10 languages. And that's many popular languages, so you can build your own tools using any popular language. It can be Visual Basic, Perl, Rust, Haskell, Ruby, Python, Java, Go, .NET, Delphi, and so on. And among these bindings, I only build Python binding, and all the rest are built by community. So writing tools for unicorns also very simple, easy. So here's one simple code in Python. You can see that first one we need to specify which code you want to emulate, which is 2 bytes here. Then you specify where you put that code to emulate in the memory. So the rest here. And then on this slide, you initialize the emulator. So here I want to have the emulator for Intel 32-bit, right? After that, I map the memory because emulator need memory, right? I need to have memory to run my code. So on this slide, I map 2 megabyte memory as this array. And then I write the code 2 bytes here into the memory, right? And then I set up the CPU context before the emulator run. So on this July, I set the value for 2 register ECX and EDX. And then I run the emulator, that's it. I run the emulator for 2 bytes from array here. And then the emulator stop and done. And on the next few lines, I print out the CPU context after the emulator run. So we get the new CPU register of ECX and EDX here. And also you can look at the memory. You see the new memory value after this emulator run. So there are many applications built on top of Unicorn. And here I only list the most interesting ones. So we have radar. Radar use capstone inside and also use Unicorn inside. Usercon is a very interesting tool that can emulate the binary from anywhere to run anywhere. So for example, your machine running Windows on Intel, you can emulate binaries coming from Linux built for ARM, for example. This one another tool built to analyze Windows shellcode. This one interesting. This is a plugin for IDA Pro to emulate code. And I think so far this only emulator for IDA that can emulate all the CPUs that Unicorn support. And you cannot have any other emulator for IDA that support, for example, ARM64 or MIPS besides this tool. And this one is built on Unicorn. Roper, another tool for rope gadget to write exploit using Unicorn inside. Anger, I mentioned before. It uses Unicorn inside and it speeds up the performance by like 600 times. Manticore, a new framework, also for dynamic binary resist, and it is Unicorn inside. Tiny antivirus, this one is on open source AV, and it uses Unicorn inside to emulate the binary, to emulate the malware. So you can detect the malware and it runs inside the emulator. And there are a few other tools built on Unicorn. And yeah, also Cuckoo. Cuckoo Sandbox, they also use Unicorn inside to detect Windows shellcode. So for the rest of the application built on Unicorn, you can look at the homepage of Unicorn frameworks. Future works. You want to support all the architecture supported by Quynh, which is like 18 architecture so far. Unicorn only support 6 now, but I want to eventually support everything that Quynh can support. I want to optimize Unicorn for better performance, and want to catch up with the latest version of Quynh, which would take a lot of time. Okay, the next part is Assembly framework, Keystone. This one is new, the latest one, built last year, 2016. Okay, assembler is the only missing piece in the Trilogy. So far you have this assembler to convert from binary to assembly, right? You have a Unicorn to emulate the binary. So the last missing piece that sometimes you want to generate new code. That means you want to generate code from assembly. So given the assembly, you want to compile it and get back the binary. So you can rewrite the code, for example. So assembler is a tool that as an input, you give it the assembly code. The assembler will compile the code and give back as output the binary. So for example, it will give the input this instruction for Intel, increase EAX. As the output for 32-bit, the assembler will return 1 byte, which is 40. So yeah, assembly framework is, can be very useful for dynamic machine code generation. So you can rewrite the binary, you can compile the binary, and after that you search the binary. So now you want to build a new assembler. That's a lot of things. So it's the same thing. You need to understand the CPU very well. You need to catch up with the latest CPU instruction, and that's a lot of work. So in 2016, last year, I started to look for some assembler framework for my own project, but nothing is good at that time. So I could find some assembler framework for Intel, but they're all outdated. So the one thing at that time is Yasmer, which is not supported, not developed for a long time. They stopped developing for a long time. And there's one framework from Intel, XED, which was open source recently this year. But unfortunately, why this one is very good, it only support Intel x86 and nothing else. If I want to have framework, assembler framework for ARM, for ARM64, for MIPS, for PowerPC, for Spark, just nothing. So again, I want something that can do a lot of things. It must be a true framework, so you can build independent tools on top of that. It must support all the popular architectures. It should run anywhere, Windows, Linux, Mac, Android, iOS, and so on. It should be updated with the latest CPU instructions. And it's built in, the core should be built in C or C++, but you should have bindings for popular languages like Python, Ruby, Java, and so on. So without the assembly framework, people struggle for many, many years. Because when you want to compile by assembly code to get back the binary, you have to use some assembler tool, not framework, because there's no framework. And at the output, the tool gives you the binary, which is some like object code. You need to extract the binary from inside the object code. So there's a lot of like steps. It's ugly and inefficient. And you can do this way, but you have very little control on the internal process of all the steps here. And the cross-platform support for this kind of methodology is very poor. So how I design implemented Keystone. So again, I fork LVM. So I used to fork LVM to build Capstone, right? Now I fork LVM to build Keystone assembler framework. And I also use MC component of LVM. Because MC doesn't only have disassembler inside, it also has assembler inside. But again, there are many challenges. First one, MC has many things, but I only want assembler component. So also at this step, it took a lot of time for me to read source code of MC to check out only the assembler framework from MC to build Keystone. The other challenge is same again, like Capstone. LVM is compiled to multiple binaries, but you want a single binary that support all the architectures. So here it took me a lot of time to modify the linking setup of LVM to build Keystone. So as the output, you have only one single library for the framework. The next challenge is that the code generated by MC, by LVM is actually for linking, because after linking, there's after compiling using MC, you can use MC to compile assembly to get back the binary, but that's not the final step because there's still one more step. That's the linker, right? Linker will generate the final binary, and because of that, the output of MC is not the final code. So, for example, if you compile this one using LLVM, the output is something like this, and they have A. The last 4 bytes is not determined because the last 4 bytes will be determined by linker, right? So MC of LLVM doesn't give me the output, the final output I want. So in this step, it also took me a lot of time to build the fix-up phase, to make the new fix-up phase inside MC, so I can detect and I can generate the final output. I don't need the linker. The another challenge is that MC of LLVM, is not aware of the branch target for some branch injection. For example, for ARM, we have this injection. This one will jump to this arrest here. And if you use LLVM to compile this code, you have this output. But actually, the output is not correct because the output actually depends on where you stay in the memory. If you stay close to where you jump to, the output is different. If you stay very fast, the output is different. So it's kind of relative branch injection. So for Keystone, I had to change the core of MC so we can return the rest of each statement in the input, and I fix on the output. The other challenge is that LLVM, when you see the invalid input, it just give up and quit and crash out, which is not acceptable for a framework, right? So here, for Keystone, I had to fix all the exit, and I do not quit, but I propagate errors back to the API. And there's some other issue. For example, LLVM doesn't support non-LLVM syntax, so I had to do that. For example, I have to support NASMer or MASMer syntax, and I need to build bindings from scratch because LLVM doesn't support Python, Ruby, Java, and whatever. Some milestone. Okay, so for Keystone, it's interesting because I run Indigo campaign to get the fund for this project. No more time for me? Okay. And I successfully funded by Indiegogo, and the first release for Keystone was last year, April, and the latest version was released last July, and I made a talk on Keystone in the last Black Hat US last year. So Keystone support 8 architectures now, and we have 11 binding language. So we can use any language here to build your tools on top of Keystone. No more time, I skip some more slides. And there are many tools, many innovative tools built on top of Keystone. You can find that from the homepage of Keystone. Future works. I want to read the first stable version very soon, version 1.0. So here's the whole circle. You can see that given the binary, you can reverse the code back to assembly using Capstone. You can modify the assembly and compile it back to binary. And you can send the binary to the emulator to run it to understand what is going on in the code. I also use my own tools with the Trilogy. First one, the key patch is an open source IDA plugin. So you can modify the binary inside IDA with key patch, and because key patch uses a Keystone below, it allows you to modify the binary for many architecture. This one's new. This one's not released yet. I built another thing named Scorpio Engine, which is binary instrumentation framework, and it supports multi-platforms. It supports multi-architectures. It's very flexible, and it's super fast. It's like 100 times faster than existing binary instrumentation frameworks that you can find out. So I hope to have another talk on Scorpio very soon and release that to the public. Finally, there's one more tool. I built some guided fuzzer for binaries based on AFL using capstone and keystone inside. And one special thing is that this fuzzer run on many frameworks and run on many operating systems, support many architectures because of capstone and keystone. And it's smarter, it's super fast, it's like 20 times faster than the fastest fuzzer you can find for binaries now. So you can see it on the screen here. It's pure software-based, so you can run on any machine without having the latest CPU, without having the special OS. So here's the performance. You can see that the execution speed is 82, which is very, very fast for binary fuzzing. Conclusion. So I built the reverse engineering Trilogy in the last 4 years. And I think that it really pushed reversing tools community to the next level. So my frameworks are on open source, support multi-OS, multi-architectures. Each of them function independently, but they complement each other very well. So the Trilogy already lays the foundation for many innovative security tools or community. So we look forward to many interesting, exciting tools in the future coming out from the top of this Trilogy. By the way, I have many stickers for the Trilogy, and if you want, you can see and pick up from me after my talk. References. Thank you for everybody to support my work in the last few years. And we are looking for new contributors, and also looking for the companies that use Trilogy, so I can keep working on this in my spare time. Subscribe win-win for everybody. So if you can help, you can support the projects, please contact me. Questions? I think I have 1 more minute. Any question? Actually, only me taking care of all the projects, and all everybody else are contributors. Sometimes they show up, they see something that they want, they contributed code, but nobody like stick with the project. So only me taking care of everything. That's why I need support. Any other questions? No? Thank you. Yeah, so anybody want sticker, please see me.